Hello, and welcome to this presentation, Getting Started with the LMG600 Vector View. In this presentation, we'll show how to configure, display, and interpret vector, or phasor diagrams, using an LMG600 series precision power analyzer. This presentation assumes a very basic understanding of vector or phasor diagrams. If you're not familiar with this topic, or if you'd like a brief review, you may want to watch the presentation Understanding Phasor Diagrams before beginning this presentation. On the LMG, Vector View is accessed by pressing the Graph Front Panel key and then selecting Vector from the available tabs. Vector View is normally used with multi-phase measurements, and measurements are therefore shown on a per-group basis. For a basic three-phase power measurement, this means that prior to making measurements, all three phases should be placed into a single group. Although we're going to focus on three-phase applications in this presentation, please note that Vector View can also be used for single-phase measurements, as well as for measurements of systems that use more than three phases. This is the main Vector View display. At the top left are the scale settings, which show the magnitude per division of each ring in the graph, as well as the fundamental frequency, here just under 60 Hz. Below this are the per-phase values of voltage and current in terms of both absolute magnitude and relative phase. Note that on the LMG, the reference or zero phase is at the straight up or 12 o'clock position. In the graphical representation, there are 6 lines, 3 showing the magnitude of each phase voltage, and 3 showing the phase currents. A combination of letters and numbers is used to designate each line. For example, U1G1 is the voltage for phase 1, group 1, and I2G1 would be the current on phase 2 of group 1. There are several parameters that can be used to configure or adjust how the vector graph is displayed. The most useful of these is AutoFit, which scales the vector diagram automatically. This can be set to fit either all vectors or only selected vectors. Note that the voltage and current can also be manually scaled. The vector diagram allows cycling through up to 3 tracks, which are essentially independent diagrams with independent values and settings. And finally, the Harmonics menu item allows the display of harmonics in vector form, with the user selecting which harmonic order to graph. Next, let's look at a few examples, starting with an ideal vector diagram for a purely resistive three-phase load. In this case, the voltage vectors and currents for each phase have very similar magnitudes, respectively, and the 3 phases are separated by approximately 120 degrees. Again, this is an ideal case and would only be seen if the load were purely resistive. A more realistic graph, such as the one where the load is inductive, will have some phase displacement between voltages and currents. Here, the voltage and currents have very similar magnitudes in each phase, but because the load is inductive, the current in each phase lags the voltage by approximately 10 to 15 degrees. Note, however, that even though each current is lagging its voltage, all 3 currents are still separated by angles of approximately 120 degrees. Here we see a somewhat different situation. The voltage and current phases are still separated by an angle of approximately 120 degrees, and the magnitude of the voltage is similar in each phase. Note, however, that one phase, phase 3, is carrying almost twice the current as the other phases. This can be seen in both the table of values as well as in the graph. A current imbalance in a 3-phase system is usually undesirable, and can often lead to serious problems, such as overheating, loss of torque, etc. Vector diagrams can also be used to diagnose measurement connection issues. For example, here the current on phase 3 is 180 degrees out of phase from what we would expect, and this usually indicates that the current clamper sensor is connected backwards. Similarly, if phase 3 were not connected at all, this is easy to diagnose from the vector diagram, since the current vector has a length of 0. More complex situations, such as one or more phases being bridged together or being connected to ground, can easily be diagnosed using vector diagrams. Let's end with a brief summary. Vector or phasor diagrams are one of the graph types supported on LMG600 series precision power analyzers. These types of diagrams are primarily used for analysis and troubleshooting of three-phase power systems and applications. On the LMG, this view shows both numerical and graphical representations of voltage and current, as well as the relative phase angles between them. In a typical balance system, the voltage phases are separated by 120 degrees, and the current phases are also separated by 120 degrees. Although in the common case of inductive loads, the current will lag the voltage in each phase. One additional application of vector diagrams is troubleshooting connection issues, such as having a current sensor connected backwards. This concludes our presentation, getting started with the LMG600 vector view. If you'd like to learn more about vector or phasor diagrams, power analysis, or power analysis solutions from Rohde and Schwarz, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.